When the two surfaces are not moving relative to each other, they are in a static situation. When the two surfaces are sliding, it's a kinetic situation. And you'll notice the static is always going to, the mu of static is always bigger than the mu of kinetic. Right? It's harder to get the box to start to slide than it is to just keep it sliding. How many have ever pushed a box across the floor? Right? You got to really push hard to get it started, but once you get it started, it's easier to keep it going. That's the mu s and mu k thing. All right? Now, force normal. What does force normal have to equal here? If you look at my picture, right? When I do my m2g cosine theta and m2g sine theta, those two vectors replace that one. I went from 1, 2, 3, 4 vectors to 5, but my 5 vectors are all friendly. All right? T1, T2, and my 73.5 are all parallel to the incline. M2G cosine
Renthia
theta.
Clements, please call 8634. Renthia Clements, please call 8634.
Is into the incline. Force normal is out of the incline. What did these two forces add to? 0. How do you know they add to 0?
Because the weight's not flying into space or crashing through the ground.
Exactly. When I put this on here, no, it's not. That's going to slide. Okay. Force normal is a smart force. It only provides enough to make the net perpendicular 0. Because could this clipboard provide more force than what the normal force is now? Sure, because if I push down, doesn't the clipboard push back? So it could provide more, but it doesn't. Because if it provided more in this situation, it's exactly right, the roll of tape would be flying off. Okay, do y'all follow? That wouldn't be a nice situation, right? I want you to walk across a floor that shoots you to the ceiling every time you touch it. It won't be fun, right? Boom, ow. And then what do? You come back down, boom, and it goes back up again. You're not going to live very long. But what does force normal do? It provides just enough. I mean, think about this. If all of you were standing on the floor right now, wouldn't the floor be giving you just the right amount of force normal? And yet it gives me just the right amount too. If it gave you my force normal, what would you do? Hit the ceiling. That makes sense? Okay? So force normal is really, really smart. All right? So what is m2g cosine theta? I'm going to do 15 times 9.8 times the cosine of 30. Not possible. 127.3. You forget the 100, that's not going to be a good thing.
That's true.
All right. So what is that going to make my force of friction static and my force of friction kinetic? Well, my force normal is 127.3 newtons. So 127.3 times 0.37 and then times 0.15. So for the static, what do we get? What is it?
47.1.
47.1 in kinetic?
Oh. Sorry, no, that's what we're doing.
Less than half of that.
19.09.
19.1. We'll just do this. All right. Now, my system is M1, M2, and M3, and I'm holding it at rest. And we're going to let go. And the question is, does it move? Well, if it was frictionless, who would win? M3. It's going to go that way, right? So, if I'm going to get friction, which of course I am, my force of friction is going to be down that way. What's the difference between 122.5 and 147? So I'm looking at 147 minus 122.5. 24.5?
Yes.
All right. We're going to talk about forces of friction. Is there friction between my clipboard and...
Yes.
How do I know? Because I can tilt it and it doesn't go anywhere. So let's say this is exactly horizontal, right? If this is exactly horizontal, is there a force of friction needed to keep the tape on the clipboard?
No.
No. But if I blow on it, is there a force of friction needed?
Yes.
Yes. How much force of friction is needed when I blow on it?
Probably not a lot.
Probably not a lot, but wouldn't it be equal to the force I'm blowing on it? So force of friction is the static force of friction is a smart force. It's only going to, I mean, how about this? I blow on it and it hits me in the nose.
That wouldn't be fun.
Wouldn't be fun. It would also be really, really weird. Right? So the force of friction, static, only provides enough force to make it zero. So let's look at the situation that I have. Right? M3 is winning by 24.5 newtons. I have 47.1 newtons of frictional force available. Can my 24.5 exceed 47.1?
No.
No, then it's not going to move. And my force of friction, it will be static, is only going to be equal to 24.5 newtons because this is force of friction static maximum. When you solve for mu times force normal, and it's the static, you are solving for the maximum possible. All right, I'm going to go over 330, but not by much. You're solving for the maximum possible here. All right? How much do I have to use? I only have to use 24.5 because that's going to net everything to zero. But for the purposes of this problem, that's boring. So here's what I'm going to do. I am going to give it an initial push. My velocity is up the slope. Okay? So my initial velocity is up the slope, and I want to know what my acceleration is, what T1 is, and what T2 is. And guess what? If it's moving, that's gone. If it's moving, that's gone. Because if it's moving, it's not static. But I do have the 19.1. All right? So, my force of friction here, 19.1. All right, my free body diagrams are complete. Once I have written a free body diagram, the next step is to write Newton's second law equations. What is Newton's second law?
F equals ma.
F equals ma. That's the basic idea. But what's the F? The F is the net force. Who's winning? Who wins here? M3 wins, so it's accelerating that way, yes?
Yes.
Since it's accelerating that way, who wins here? Doesn't T1 win? All right. So my M1 equation is going to be T1 minus M1G equals M1A. This is the net force. I'm adding my forces together. If I'm adding my forces together, why is that a minus? Because T1's up and gravity's down. They're oppositely directed. How do you add vectors that are oppositely directed?
Subtract.
You subtract. So this is still the net force equals ma. It's the F equals ma. All right. I'm going to do the M3 next. Do three different colors. M3. Who wins here? M3G. So I've got M3G minus T2 equals M3A. Do you follow that that's my M3 equation? It's the net force equals ma?
Yes.
Okay, so now we're going to do M2. My M2 equation. Who wins? What direction is the acceleration for M2? Up the incline. What's the only force going up the incline? Isn't it T2? You gotta go, you gotta go. I understand. So I have T2 minus T1 minus M2G sine theta minus mu K M2G cosine theta equals M2A. Look at all my forces. I have 1, 2, 3, 4, 5, 6 forces. Some of the forces has to have all the forces in it, but what do these two forces add to? 0. So do I really need to write them? No. So how many forces are left? 1, 2, 3, 4. On the left side of the equation, I have to have four things. And I have 1, 2, 3, 4. I have T1, T2. This is the component of gravity down the plane, and this is the force of friction down the plane. Equals MA. Add them up. Doesn't a positive T1 and a minus T1 cancel? A minus T2 and a positive T2 cancel? So I'm left with M3G, wasn't that the winner? Minus M1G, a loser, minus M2G sine theta, a loser, minus force of friction, which always loses. I mean, that's the whole point, it's negative, right? And what does that equal? That's going to equal M1 plus M2 plus M3A. And in that equation, there's only one unknown. Acceleration. Solve for acceleration, and you win. Plug acceleration back into here and solve for tension. Plug it back into here and solve for the other tension. All right. We need to do a bunch of these before you will be comfortable in doing them. But this is the ultimate because this has everything in it. That's why I wanted to do this first one. All right, you will get much more used to this as we do more of them, and Atwood machines and different things that show up on UIL tests. All right, any questions? Did you learn something today? I hope so.